Welcome to the next set of videos on gases and gas laws. We're going to start with a brief introduction to states of matter and a brief introduction to the kinetic molecular theory, which will explain the properties of gases. In elementary school, you may have been taught that there were three types of matter. The first is a solid, which has a fixed volume and a fixed shape, and the atomic level has the atoms tightly packed together. So basically all they can do is vibrate next to each other. Then you were taught that there were things called liquids, which have a fixed volume but a varying shape. You can pour them. The atoms are close to each other, but they're able to move past each other, which allows the liquids to flow. Last, there were gases, which have an indefinite volume and an indefinite shape. And the atoms or molecules are so far apart from each other, they really don't interact, and so they don't stay cohesed, and they become a gas. And it turns out that that solids can melt and become liquids, and liquids can evaporate and become gases, and gases can condense and become liquids, and liquids can become solids. But when you were in middle school, you may have been taught that there were four types of matter, and added to the previous three, there were plasma, which is hot ionized gas, which at the atomic level means the electrons are stripped off of the nucleus, and they all float around together. And this is some of the most common matter in the universe because it's what makes up stars. But it turns out that in actuality, that is all incorrect because there are really at least 7 types of matter. The additional 3 is something called a Bose-Einstein condensate, which is a state of matter that occurs at almost absolute zero. The quark-gluon plasma, which is a state of matter that occurred shortly after the Big Bang. And lastly, degenerate matter, which occurs at the center of very dense stars, and there have been reports of other states of matter also. We're not going to get into those 3 because those all involve quantum mechanics. But this section is on the gases, and to understand gases, you need to understand the kinetic molecular theory. But this theory is a very good way to explain why gases do what they do. And it turns out that the properties of gases are due to the fact that gas molecules are in constant motion, and that there are 6 assumptions that we make. The first is that gases are composed of such small particles, it can be assumed they have no volume. The second is that the molecules are so far apart from each other, relatively speaking, there is no attractive or repulsive forces between the gas molecules. The gas molecules move in a rapid and random fashion. They move in a straight line until they hit something. Then they bounce off, and those collisions are completely elastic. No energy is lost. For any given gas at a given temperature, the kinetic energy is the same. The speed of the molecules is not the same for different types of gases, but the kinetic energy is. And it turns out the kinetic energy is directly proportional to the temperature in what is called the Kelvin scale. If you double the Kelvin temperature, you double the kinetic energy. Temperature, which by the way is a measurement of atomic or molecular motion, has several scales, as you know. We've been using the Celsius scale. I've told you not to use the Fahrenheit scale. But for gases, you need to use the Kelvin scale. The Kelvin scale is an absolute zero-based scale. The lowest temperature that you can get on the Kelvin scale is 0 Kelvin, which is absolute zero, which is where all motion, even at the atomic level, stops. For the record, it's impossible to get to absolute zero, but they have gotten down to the nanokelvin. When you're dealing with gases, you must express the temperature in Kelvin, and it turns out that Kelvin is the temperature in degrees Celsius with 273 added. For example, if something has a temperature of 29 degrees Celsius, what's the temperature in Kelvin? Well, Kelvin is degrees Celsius plus 273. The temperature in Kelvin will be 29 plus 273, which is 302 Kelvin. So 29 degrees Celsius is the same as 302 Kelvin. So here's one for you. If something has a temperature of 147 degrees Celsius, what is the temperature in Kelvin? Go. And the correct answer is 420 Kelvin. How do we get that answer? We start with the basic expression. We plug in the 147 where it belongs, add them together, and you get 420 Kelvin. So 147 degrees Celsius equals 420 Kelvin. How about going the other way? You have a temperature of 559 Kelvin. What's the temperature in Celsius? Go. And the correct answer is 286 degrees Celsius. We know the expression, Kelvin equals degrees Celsius plus 273. Plug in what we know, 559 Kelvin equals degrees Celsius plus 273. Subtract 273 from both sides, and you get 286 equals the degrees Celsius. Now, when it comes to gases, we measure pressure, and pressure is a measure of force per unit area. You may be familiar with this as pounds per square inch. Force, which is pounds per divided by the square inch, or PSI, which is the measurement that is used in tires. But we're not going to use PSI or the English system at all. From a molecular viewpoint, pressure is the number of collisions of gas molecules with the container wall per second. The more collisions per second, the higher the pressure. The units of pressure that we will use are the following. The kilopascal, which happens to be the SI unit, but very frequently people will use the atmosphere, the torr, or millimeters of mercury. At sea level, we say that that is equal to 1 atmosphere. 1 atmosphere is the same as 101.3 kilopascals. Both of those are equal to 760 torr, and those are all equal to 760 millimeters of mercury. Yes, torr and millimeters of mercury have the same measurement. This allows us to change between various units. So, for example, if we have a gas where the pressure is 475 torr, what is its pressure in kilopascals? This is a dimensional analysis problem. We know that 101.3 kilopascals equals 760 torr. So 475 torr times 101.3 kilopascals divided by 760 torr. Notice the torr cancels out. Equals X, which is the pressure we're interested in. We get 63.3 kilopascals equals X. So we can say 475 torr equals 63.3 kilopascals. Here's one for you. If the pressure of a gas is 349.5 kilopascals, what is the pressure in atmospheres? Stop, figure it out, come back, and check your answer. Go. And the correct answer is 3.45 atmospheres. How did we get this? We know that 1 atmosphere equals 101.3 kilopascals. So 349.5 kilopascals times 1 atmosphere per 101.3 kilopascals equals X. Do the math and you get 345 atmospheres equals X. So we can say that 349.5 kilopascals equals 3.45 atmospheres. Now pressure depends upon 3 things, and we'll bring in the kinetic molecular theory to explain these. The first is the volume of the container. This is provided to keep the temperature and the number of molecules the same. So here we have a container. It has 10 gas molecules. The temperature is 298 Kelvin, and the volume is 5 liters. We then cut the volume in half, but we still have 10 gas molecules, and the temperature is still 298 Kelvin, so the speed of the molecules hasn't changed. However, because the container is smaller, the molecules have to travel a shorter distance, so there are more collisions per second. So pressure goes up because pressure is collisions per second. So volume matters. The second is to increase or decrease the temperature. This is if you keep the volume and the number of molecules the same. Remember, temperature is an indication of speed. So we start with our original container, but this time we increase the speed by raising the temperature to 400 Kelvin. Keep the volume the same. At 400 Kelvin, the molecules are moving faster, so more collisions per second, so the pressure goes up. And the third is the number of gas molecules. So assume you have 10 gas molecules at 400 Kelvin with a volume of 5 liters in the container. If we double the number of gas molecules but keep the temperature the same at 400 Kelvin and the volume the same at 5 liters, you have more molecules, so more will be colliding with the wall at any given time, so the pressure goes up. Note, the pressure does not depend upon the type of gas. 2 different gases in the same size container at the same temperature with the same number of molecules will have the same pressure. Pressure simply depends upon volume, moles, which is measurement of how many, and temperature. It is independent of gas identity. So to review, gases have a variable volume or shape. We can use the kinetic molecular theory to explain gas properties. And there are 6 assumptions: that gases are so small they have no volume. There's no interaction between the gas molecules. They ignore each other. The gas molecules move rapidly and randomly and will move in a straight line until they hit something and then they switch direction. Those collisions are completely elastic. No energy is lost. The kinetic energy is the same for all gases at a given temperature in Kelvin. The kinetic energy is directly proportional to the temperature in Kelvin. Remember, for gas problems, the temperature must be in Kelvin. Kelvin is the temperature in Celsius, plus 273. Pressure is the number of collisions of gas molecule with the container wall per second. And the units of pressure, which we will use, are kilopascals, atmospheres, torr, and millimeters of mercury. And here are the equivalency statements for all 4 of these pressure units. The pressure depends upon 3 things: the volume of the container, the temperature in Kelvin, and the number of gas molecules. Pressure does not depend on the type of gas. In the next videos, we'll begin to examine the relationship between pressure and volume, temperature, and number of moles.